أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله. Welcome back. This is a tutorial video actually. However, the tutorial video will help you also to do your project. After this video, I will post another video that how we can um, implement this theoretical filter in the ADS and from there you can build up your project. However, that's later on. Today's topic is again the microfilters. In the previous lecture from lecture 10 to lecture 15, we learned how to calculate uh, the filters, different filters such as the low pass filter, the prototype low pass filter, the high pass filter, the band pass filters. So there we learned all about the circuits with the capacitor, inductor, and so on and so forth. However, for the microfilters, we can really design a microfilter on directly on PCB without any capacitor and inductors, only with the microstrip transmission line. So our filter implementation to this tutorial video is for that technique. So we will learn how to convert our lumped filter design, which is capacitor and inductor design, and we convert it to the microstrip passive microfilter. In this video, we will learn about the prototype low pass filter. So let's go back to the same example that we had in our previous lecture on microfilter design, which is this one. So this was the characteristics of the design. So we have asked that at cutoff frequency 2 gigahertz, the impedance is 50 ohm, and at 3 gigahertz, we have a 50 dB insertion loss. So this is the insertion loss method that we already gone through about it in our previous lectures. But I will just quickly go through that with these specs that what we have here, all the specs here, 2 gigahertz, our cutoff frequency. Insertion loss is at 3 gigahertz, we have 15 dB, which is maximally flat. So with this, we have, we need to calculate this one, and then we find out this is 0.5. So with 0.5 and then 15 dB, now we're going to go and see what is our order. So from here we plot. So with 5 and 15 dB, we find out that our order is 5 order, fifth order. So from the table, we find out that our fifth order elements are like this. This is G1, this is G2, this is G3, G4, and G5. So this part we already know, and then from this part, finally we are here. In our design section in the previous videos, we learned about that after this we can convert this C1 L1 to real capacitor inductor values. So there are some process that you already know if you've gone through those videos. But in this implementation video, we will not go towards that one. From here, we will choose a separate path, and from this path, we will learn how we're going to implement this one into a PCB. PCB means the passive microwave filter without any capacitor inductor elements, only the transmission line. So from here, you're familiar with, so this is actually G1, and this is G2, G3, this is G4, and this is G5. Now to do so, we need two different steps. One is we need to learn about the Richards transformation that we will learn first, and then we're going to learn about the Kuroda identities. So let's go to the Richards transformation, where the Richards transformation actually transform this individual circuit element to a different transmission line combinations. From the Richards transformation, then later on, among the transmission line, we will rearrange by using the Kuroda identities. So let's go to the next slide. Okay, so this is the our circuit so far. We have G's, all the G's like G1, G2, and I already told you until G5. So if we encounter any capacitor with the Richardson transformation, Richards transformation, we can convert this capacitor to the open circuited stub. This type of open circuited stub we learned in the matching networks and tunings. We learned about it already, this open circuited stub. And if we have any inductance or inductor, if we encounter an inductor, then it transfers it to a short circuited stub. Usually this is called the shunt stub and this is called the series stub. Then what would be the impedances of this one? Since these are all normalized values, so if we have a normalized value of G, any G here, let's say here you have G2 and G4, so it will directly give the value to here. So if we have G2 here, so 618, so here will be 1.618. On contrary, if we have a capacitor, it will convert into a shunt one, which is a parallel stub, which is open circuited, will be here with a 1 by G value. Means if let's say it have a G1 here, so here it will be 1 point, so it's 1 by 0.18 is 1.618 here. So that's how the Richards transformation works. So let's try now individually that from here we will get something like this, which is one more thing is however this impedances here actually defines the width of this transmission line, but what about the length? The length of the transmission line is the wavelength divided by 4. Later on we will discuss about it. You know about it. This wavelength divided by 4 actually the physical length. So whatever frequency is, let's say we have a frequency of here it's 2 gigahertz, right? So from here we will have a wavelength. So from that wavelength, actually we can find out what is our length of this one. So we will have a 2 gigahertz wavelength here. It will have some millimeter value, and then we will divide with 8. Then we will get the value of L. So all the stubs that we're gonna add due to the Richards transformation or in the future in Kuroda identity, all will be having the same length of lambda by 8. So remember this one. Later on I will reflect upon this one in this video. So now we go and see how it converts. So here, so we have C. So for C, we have the open circuit stub. For L2, this is an inductor. So we have a short circuit stub, and so on. We have one more here because of the C, and one more here because of C, and because of L, we have this one. So we have 5 different stubs here, which is one is open circuit. This is open circuit, this is open circuit, and this is short circuit, this is short circuit, which is in series, and this is in parallel, and parallel. So this is our first build up So when we do Richard's transformation, we from this 5 element we get 5 different stub. Now actually we can use this directly, but well, since we need to know the whole thing, that how actually we need to change from this open circuit stub to the series stub, and then series stub to the open circuit stub, from interchanging between the transmission line to the stubs, inter stubs, like from open to short and short to open. Later on, after this slide, we will learn how the Kuroda transformation can be applied. But what about the values? The values I already told you. The C value will be 1 by C, means the G value actually. So the G value will be 1 by G, and sorry, this G value will be 1 by G, and this G value will be same as the G. So let's see what's the values. Here is the value. So since we have a G here, so this is 1 by G, so 1.618, and this one is 1.618 because G2 here. G3 is this one, so 1 by G3 is 1 by 2, and this one is the similar. So this is what we get after the Richards transformation. Now from our goal will be to transfer this one into this stubs. So we will learn how to transfer these stubs to open stub, to short to open. So in the next slide, we have our Kuroda identities. Basically, from the book, we have four different Kuroda identity, and from the book, I have changed a little bit here. Here, these two places are changed because for your convenience to understand. Usually they put 1 by Z2 and 1 by any square Z2, which is actually a little bit confusing. So I change here as a Z2. I will obviously tell you what this signifies, but for you to demonstrate that, for your demonstration purpose, these are the four identities where we will learn these two. These two identities basically similar, but these are for the more complex problems. So we will cover these two, which will be well enough for this filter implementation. So here we have these two identities. One belongs to the this is capacitor, right? So this is usually belongs to this. So if anything capacitor, this represents this system, and anything which is inductor, which represents this system. So we go here again. So this is the capacitor, means this is the open circuit stub, and we have a transmission line. So if we have this combination, so we can actually convert this one to, this one can be converted here into, this is a open circuit stub, right? So this open circuit stub will be converted into a short circuit stub, and the transmission line will come here. So it will shift here, it will go here, and it will become a series stub, and this transmission line will come here, shift here, and as it will stay as a transmission line. But what will be the impedance? Impedance will follow like this. So we have a Z2. So Z2 will be, we will take the Z2 values, and Z2 divided by N square will be the value of this transmission line here, not here. This will be equivalent to this one. So this will be equivalent to this one. But now what is the N square here? The N square is this one, which is really important to understand, is 1 plus Z2 divided by Z1, Z2 divided by Z1. So N square you need to calculate, and when you're going to move them around, so it will act upon. So if you have a shunt stub, parallel stub, then all, if you want to convert them, all needed to be divide. Remember this one. In similar fashion, if you have a open circuit, short circuit stub, which is this one, so in similar way, it will shift here. and this will shift here. So it will become a open circuit stub, and then the impedance will change according to this one. So we need to find n square, and then we multiply with Z1, since um, this is a stub and this is a transmission line. Remember one thing, if you are converting, if you are actually shifting this one, you need to find out the transmission line impedance. You need to always use the stub impedances to find it out with n square. So here, similarly, this we use this one and multiply by n square to find out what is the transmission line impedance, and this will convert here and use this Z2 multiply by n square to convert it to shunt stub. Uh, this is a demo, this is just a demo, but it will be better understand in the next slide. Sorry, not here, but there is one like what I call it a tips like this. How you're gonna find out what is Z1 and Z2 is that, let's say it's a shunt stub. If it's a shunt stub, remember the transmission line impedance is always Z1 and the shunt stub is always Z2. In the opposite way, if it's a series stub, you need to remember the transmission line impedance is always Z2 and the transmission and the series, sorry, this is a spelling mistake, I think. Series stub impedance is always Z1. And that's how thus we gonna find out what is our n square. So if you change it around, and if you confused between this calculation, then you will have an inaccurate n square, which will lead to inaccurate values of your filter. So let's go to the next slide. Now we see we give a real demonstration on how this can be implemented. So this is the scenario first. The case one is shunt stub following by a transmission line. So you have a shunt stub here, which value is impedance value is Z2, which is 1.618 Z2, and we have a transmission line which is Z1. We need to consider, because just I told you this you need to follow. So here we have Z1 and Z2. Then we need to find the n square. So we find the n square is 2.618. Now how this will come here and this will go here. So this will become a series stub and this will become a come here and become a transmission line. How? So when we are actually calculating this one, we need to use this value. So I told you that if you are in a shunt, you want to convert it to series, you need to always divide it with n square. That if you are finding the transmission line impedance, you're going to use the impedance of the stub and divide it into n square. So this divided by n square gives us this value. So Z2 divided by n square gives us the value of this one, and Z1 divided by n square gives us the value of this one. So now we have a from shunt to series stub, which have a value of 0.38, and a transmission line which value of 0.618. In similar cases, if it's a transmission line followed by the shunt stub, the same thing will happen. These values will only this one will go to here. Yeah, that's all. So this is another case. Now we go to the shunt implementation. Sorry, series implementation. So we have a series here, which is from inductor. We got it, and then we have a transmission line. As I told you before, the Z1 is this one, and Z2 is this. So because of that, we have n square is this one, and then I told you that if you want to find out the transmission line impedance, you need to use this one. This one multiplied by this one gives us this value. So we have this value, and the stub value we use this value, impedance transmission line impedance value. So we multiply by Z2 and we get this value. In similar way, if a series stub, if a series stub followed by a transmission line, this is calculations are like this. In a similar way, if a transmission line followed by a series stub, transmission line followed by a series stub, then they will just interchange. So from here, this will come here only. This will remain the same. So there are 4 combinations it can be. From here, here, it will interchange. This will be like this, and here we find out. So with these combinations of knowledge, we're gonna input this one here. Here we're gonna convert this one into this one. So from here, let's see now how you're gonna convert, because there is here, you see there is no transmission line point here, right? But for our freedom of choice, we always can introduce one of transmission line here, which is 50 ohm, which is 1. So anytime we can do it, even though here we can do it also after we will see. So we need to introduce one transmission line which have one normalized impedance, which is 1. So we let us introduce this one. So now this will become a combination, as we have learned before. So this transmission line followed by the stub, and we have a transmission stub followed by a transmission line. So from here, now we are ready to find our n. So this is becoming our Kuroda identity implementation block. So from here, we find out what is our n values. Later on, you find out by yourself. I calculated for you, and then after n values, these values are, this value is representing this one, this is representing this one, this represents this one, and this represents this one. So from here, this whole thing becomes this one transmission line, and this whole thing becomes this, and then one transmission line, which is somehow these values. So this is 1, and this is remained the same, because we didn't, this 3 we didn't touch. So only this one we find out, So now after changing, we have these values, new values, and we have this remain, and these new values we have. However, this one, we need to convert it one more time, because we're gonna bring all them to open circuit stub. So to do so, we introduce again one 50 ohm normalized impedance of 1 here. So this is not here. This is not here. We only have this, and this. So we imposed 1 here. So due to this one, now we have blocks again. This is a block. This is one more block. We keep it like this because we want this one, so we don't disturb this one. We have one more block and one more block. So here is like this. So this block will give us a new n square, and this 2 will give us another, and so on and so forth. Remember one thing, that these are actually identical. So this will be easy for us to calculate. Once we calculate this one, we can have this calculation also. So similar way, since we have here, so this is our n and all the n consideration. So we get our n square z2, which is represents here, and this one n square z1, which represents here. Well, this a little bit complex, but yeah, of course, if we practice more, you will understand more, and then you will learn more. So this section here, so we have 2.23 here, and then this one is this one. So this is similar here, and this is similar here. This one. So now we have our final stage. Preparation of the final stage is all the steps are now open circuited here. So 1, 2, 3, 4, 5. So like this, our calculations are done, where we have these are normalized value of 50 ohms. So we have here this one. So normalized impedances for different stubs here. Now we add again one here because we're going to connect it to a 50 ohm line, so which will become later on a 50 ohm line. Now these all are actually the normalized value for 50 ohm. So we need to denormalize it. So we multiply each element with 50 ohm and see that we get our ohmic, all the impedance value of the transmission line. So this transmission line have a 50 ohm. This transmission line have a 180 ohm, which will be very thin because this is very high impedance. So this one is 42. This one is around 69 point something, and 111.8, and they are identical. So this one actually, if we write in a if we illustrate in a proper way, so this will become something like this. So this is our 50 ohm here. We check 50 ohm. So 50 ohm line, and this is a 50 ohm line. So now 180 ohm will be, of course, very thin line. Then this one and this one and this one. So here this one, and 42 line is much thicker, and 25 line is much thicker, and so on and so forth. Here we check. Now each of the lengths, I told you before that all of the stuff, whether this one, this one, this one, this one, this one, actually these are the same. So this one is the same of this one, the same as this one, the same as this, and so on and so forth. All the lengths are actually lambda by 8, which is a physical length. So we convert it to an electrical length. So lambda comprised in electrical length, which is 360 divided by 80, which is a 45-degree length. Later on in ADS, when we're going to implement for the simulation purpose, we will learn about this one, how to implement this one. So this is our final filter design. It will look like somehow on PCB like this, where this is RF input. So we will input our RF here, and then RF will pass through with these different transitions and different stubs. When it pass through like this, so it will give us exactly response as the low pass filter at 2 gigahertz of cutoff frequency. Here we will get it. So this is so far it looks a little bit tedious and more understanding in much understanding manner than more calculating manner. But however, it have also some rigorous calculations, but along with the understanding also. So if you have problem understanding, your calculation will end up erroneous, and then later on you will find out something very deformative design, which will end up with a non-responsive filter, what you desire and intend to do. So from the beginning, you have to concentrate, and whenever you design, you have to be very careful with your steps. All the steps you follow and you make precise, then at the end, it will become like this. So the steps needed to be very important, needed to be taken care of very rigorously and thoroughly, and with high concentration. Because step one, if you do some mistake, so it will build up. Even though you do not do mistake in step 2, 3, 4, and 5, or so on and so forth, it will build up and it will end up in a wrong circuit layout. So this is the final layout. What we're going to implement this one in ADS in our next video. So for your convenience, there are some recommended practice. Example 8.5 you do by yourself and try understand, and then the problem 8.13 and 8.14 from David Pollard, third edition you can find. And in the fourth edition, maybe you will find more example for that one. Who really want to master this one, you need to do a lot of examples for this. So So far, these are all the recommendations and explanation for our low pass filter implementation video. Uh, Here we have learned about the Kuroda first, the Richards transformation, and we learn about the Kuroda identities and how many steps. There are two steps Kuroda identity we used to convert it into this layout. So, and the next step, I will show you how to implement this one in ADS. So thank you so much. May Allah bless you all. Assalamu alaikum wa rahmatullah.